Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X published on January 31st, 2026, just about a week ago. It introduces a robust new planner called GRASP that achieves up to a 10% increase in success rates on long-horizon visual tasks, while using less than half the compute time of standard methods. The paper is titled Parallel Stochastic Gradient-Based Planning for World Models. And as we'll see later, the visualizations of the loss landscape are quite revealing about why traditional methods often fail in this setting. To understand the challenge, Figure 1 visualizes the underlying optimization problem. On the left in panel A, the graph tracks the distance to the goal during a successful task. Notice how the error actually increases midway through the trajectory, which means the agent must temporarily move away from the goal to succeed, defeating greedy strategies. The center plot, panel B, shows the resulting loss landscape for standard gradient descent, which is jagged and full of traps. In contrast, panel C shows how the new method smooths the surface into a clean, navigable slope. Figure 2 illustrates exactly how the method achieves this stability. The top panel shows the standard serial planning approach, where errors must flow backward through a long, sequential chain, often causing unstable gradients. In contrast, the bottom panel introduces parallelized planning. Here the method breaks the chain by treating intermediate states as independent variables that are optimized simultaneously. Crucially, the crossed lines on the state inputs indicate a gradient stop, which prevents the optimizer from exploiting brittle patterns in the high-dimensional vision model. Well, Figure 3 demonstrates exactly why those direct state gradients are so dangerous. On the left, panel A shows the expected behavior, where the model predicts a standard, physical movement. But on the right, in panel B, we see an adversarial example where the optimizer exploits the model's brittle geometry. By making a tiny adjustment to the state input, it tricks the world model into predicting that the object instantly jumps to the goal. This effectively teleports the object in the model's imagination, which solves the math problem, but completely fails the physical reality. Alright, so Figure 4 displays the actual trajectories generated by the GRASP planner across 3 environments. In the top left, we see the point maze, and on the right, the wall single task. The bottom row visualizes the push T task. What is crucial here is that despite the relaxed constraints and added noise, these virtual states converge into realistic, physically valid paths. They successfully navigate around obstacles, like the walls in the top row, rather than getting stuck in the greedy traps that typically plague simpler methods. So, while Figure 4 showed us valid paths, Table 1 now quantifies the performance on the challenging push T task. This table tracks success rates and planning times as the horizon extends from 40 up to 80 steps. The top rows compare baselines like the cross-entropy method, LATCO, and standard gradient descent. Notice that as the horizon gets longer, specifically at 80 steps, these baselines struggle significantly, with success rates dropping to near zero. In contrast, GRASP, shown in the bottom row, maintains the highest reliability, and remarkably, it does so in about half the time. Well, beyond just raw success rates, Figure 5 breaks down the speed of convergence. Here, we see the cumulative success rate plotted against wall clock time for a fixed horizon of 50 steps. On the left, panel A shows the point maze, while the right, panel B, displays the more complex push T task. In both cases, the solid blue line representing GRASP rises much more steeply than the baselines. This indicates that it finds valid plans almost immediately, whereas methods like gradient descent or the cross-entropy method take significantly longer to make progress. Okay, having established the speed advantage, Table 2 now performs an ablation study to pinpoint what actually drives this success. The top section looks at sync steps, which are those periodic full rollout updates. Crucially, without them, the no-sync row, the success rate collapses to just 1.6%, proving that mixing in standard gradient steps is essential for valid trajectories. Finally, the bottom section confirms the gradient stopping strategy. By blocking the gradient flow through the state, accuracy jumps from 46% up to 59%, verifying that direct state gradients in vision models are indeed harmful. Wrapping up, 2 takeaways stand out. First, breaking the serial chain into parallel virtual states allows for stable planning over much longer horizons. Second, by effectively cutting the gradients through the state, the method stops the optimizer from hallucinating shortcuts, keeping the physics grounded. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.